Good morning, everybody. My name is Spencer Ellsworth, and I am going to be talking about physics. Specifically, my question being, how fast does current travel? Right? So the question is, how fast does current travel? But first thing is, what is current? What makes current? And current is made by electrons. So if you're asking how fast current travels, you're kind of asking how fast are electrons traveling? And electrons move at 1% the speed of light. But unfortunately, they're not moving that fast through the wire. They're actually moving through the wire. Their forward motion is only 0.1 millimeters per second. And if you've ever flipped a switch, you know that that's really slow. And so that must not be what's going on. Electrons move super fast, but they move through wires super slowly. So why is that? And that is because of drift velocity. And so, the way that the drift velocity works, if you were to take a picture of it, is imagine that this is a wire, right? And you've got this little electron, and it's going super fast, but it's not going fast down the wire. It's just super chaotic because it's a particle and it's moving everywhere, right? And so it is still going super fast. But this idea is called drift velocity, where it is only moving through the wire super slowly. And so then this must not be what current is, right? So if it's not the drift velocity that's making the current that we're seeing, then what is? And what the current is electric fields. And so any kind of charged particles have a force on each other, right? Electrons repel electrons. And that force is this electric field. And so even though the electrons are not going through the wire super fast, this electric field goes through wires at a third the speed of light, which is very fast. And that is what you're seeing when you're flipping on a light switch and the light bulb just turns on. So what I always thought was happening with currents is something like this, where you have this storage of electrons, right, connected to a switch. This is my switch, and it comes up to this light bulb, right? And I always figured that you turn the switch on, which allows electrons to come all the way through and be exerted by the light bulb somehow. And it's kind of like if you were to imagine an empty hose, right? Empty hose. And you flip this switch, and water has to slowly make its way all the way out before coming out. But that's not very fast. That's definitely not instantaneous, right? And so what's actually happening is you take out this idea of a storage, right? So now you have this. You have a current circle full of electrons already, right? And so then when you flip the switch, this allows the electrons to start moving. And the movement of electrons right here is what's actually turning on the light bulb. But the important thing is, the whole wire is already full of electrons, and right when they start moving, they all do, right? Taking it back to the hose, imagine it like a full hose this time, where you flip the switch and one water droplet comes in, but it's not the one that goes out originally, right? This water droplet pushes on this one, which pushes on this one, which pushes on this one, which pushes on the final one, and the final one is the one that actually pops out instantly, right? And it's the same idea with circuits. Now we're going to do some math, because math is super important for this class and you really need it for this class. So, current is defined at the rate at which charge flows, right? So that's current. An important thing to know about all of this math before we jump in are the abbreviations and units. So something that I find really hard about this class are all of the different measurements with the different symbols and the different units, right? So we have measurements like current, charge, and time, which is all we need to figure out current stuff, right? And on any kind of formula sheet, they're going to show up as I, Q, and T. Current is I, charge is Q, time is T, and then you have SI units, A, C, and S. And what's really kind of difficult here, which is what makes this super important, is you need to know these units in order to read the problem, and then you need to know the symbols in order to find it on your formula sheet. So, with that all in mind, what current is I equals the change in Q over the change in T. Also, in units, the change in amps equals the change in coulombs per second. I got a call.
Why does the symbol not match the SI unit?
That is a great question. Why does the symbol not match the SI unit? And that is because most SI units are named after somebody, right? So the measurement for current is an A, which doesn't make any sense, but that's because the unit is named after the guy Ampere, because he's the first person to find it mathematically. Same thing with charge. The person who found charge was named Coulomb. And so that's just kind of how it is. Now we're going to do this word problem here with what I was talking about. What is the current involved when a truck battery sets in motion 720 coulombs of charge in 4 seconds while starting an engine? Here is our formula, right? I equals Q over T. I is current, Q is charge or coulomb, T is time or seconds. And so looking back to our problem, we can see that we have 720 coulombs, which would go here, and then 4 seconds, which would go there. That divided by that gives us our I, which is what we're looking for, and that comes out to about 180 amps, which is a measurement of current. Next question. How long does it take 1 coulomb of charge to flow through a handheld calculator if a 0.3 milliamp current is flowing? So we are going to use this same thing here, but we're not solving for I anymore. We already have the current and we have the charge. We're actually solving for T this time. And so using algebra, we take this and turn it into change in T equals change in Q over I. Algebra. And then we just plug in what we have here. We know that we have 1 coulomb, and then it's 0.3 milliamps, and so it's going to be 0.3 times 10 to the negative 3 milliamps, or amps at this point, right? You divide that by that, ends up with 3.33 times 10 to the third seconds. Thanks so much for watching. I hope that helps you understand how fast current flows, how current works, what current is, as well as some of the math that we're doing in this class to help you solve for current or anything having to do with current. Again, thanks for watching, and